Hello, this video is on inverse trig functions integration. Now here are the integral formulas that we will use for inverse trig functions. Now we're only using 3 forms instead of having 6 because, as you may recall, for each inverse trig function you had to have a derivative. But the 3 of the derivatives were just the negative signs from the other, like the derivative of arc cosine was the negative of the derivative of arc sine. So instead of worrying about having 6 possible answers here, any remaining negative signs or whatever would just stay with the answer in this form right here. So you wouldn't have to worry about 6 possible things, just these 3 right here. So we'll look at these for a second. I won't read these out verbally. I'll just let you look at them. And so we're not concerned with answers that lead to the other 3 inverse trig functions. So we're going to be working with those. So let's see what we got here. Now here's an example. Now I wrote the integral form down. I also have the answer over here in Maple, but we'll check that in a minute. Maple software. Before you worry about what form it's going to be, the best thing when you're approaching any kind of integral is to set it up in substitution form. Get it to be substituted, assuming it can't be integrated directly, which this one cannot. So it's more important to get all the u and du stuff going. Then you can figure out what integral form it fits. So the way that I would approach this problem, I would look at it, okay, I need my u to be something that when I take its derivative, it doesn't have a variable x in it. So that means it needs to be something times x, because the derivative of cx would just be c. And then also I'd be looking for something then that you square, since it's squared here, you would want it to square to be 4x squared. So the correct choice here would be let u equals 2x, because that will give you u squared equals 4x squared. Then you can easily make the dx fit the numerator there and be 1/2 du. And then we'd be looking for a squared, it would be 25, therefore a would be 5. So here is how it would set up then. So you can pull the 1/2 to the outside. You'd be left with du in the numerator, and then the square root of 25 minus x, u squared, in the denominator. And you can see right above that, that clearly fits the inverse or arc sine form. Obviously, both of those are acceptable answers. I don't know why I put these formulas as inverse notation, but it's just as correct as using arc. And it fits it perfectly. In fact, I went ahead and just wrote arc sine in the answer. There's the 1/2 that comes from the substitution. You have arc sine of u over a. So u is 2x, a is 5, 2x over 5, then of course your plus c. And there's what the Maple program spits out. Yeah, it's weird that the Maple program does not ever show the plus c. They just didn't bother to program that, I guess. They just decided that the user would realize there's a plus c there. But there needs to be a plus c there, because this is an indefinite integral. Now this next problem, just to kind of show you, the more you learn about integration, the more you have to kind of pay attention to other techniques and a variety of how to handle different kinds of problems. And this one looks real similar to the last problem, but it's not, because there's an x in the numerator. That means you want to let u be everything under the radical. So in fact, this integral in reality is a Cal1 integral, but I want to throw it in there just so you can kind of see, because this could have been done without any new techniques. You just let u equal 25 minus 4x squared, and then the derivative of that would be negative 8x dx. So you might be wondering, why isn't u just the 4x squared? Well, in these kind of situations, the rule is they're not separate like they were in the last one with a squared and u squared. If the decision to include the constant or not include the constant without affecting the du. In other words, the du is the same whether you have the 25 or not, but that means you include the 25 because you want to include all of it. So that gives you negative 8x dx, so that will give you negative 1/8 du as x dx. So that brings the negative 1/8 out here. And then now you just have, because you bring the radical up, and just makes it u to the negative 1/2. So this is strictly just a power rule. You know, the u to the n plus 1 over n plus 1. So we have u to the 1/2 over 1/2, flip all that over, negative 1/2 u to the negative 1/4 u to the 1/2. And then you substitute u back in there. So you see that's kind of sneaky. You know, one of those is arc sign, one of those has an x. And in chapter 8, for example, if that numerator was x squared, that's going to require a different integration technique. So the more you learn, sometimes the scarier it can get, because there's just so many different methods to approach different problems. But you can do it. It just takes practice at recognizing. Now, so once again, I'm going to look at this one. Now, because I don't have an x in the numerator, I don't want to let that entire denominator be the u, because that would, the derivative of that entire denominator would be 18x, and that doesn't help me, because I have no x up here. So now I'm going to focus on the 9x squared. And I'm going to use kind of the same logic that we used in the last problem, is that I need something that the u to be where its derivative will be a constant. So, and then when you square it, you'll get 9x squared. So then the choice would be 3x, because 3x all squared is 9x squared, and the derivative is 3. And of course, you can pull that 12 out of the way, and then 3 dx, you divide both sides by 3, you get 1/3 du equals dx. And here's a squared equals 49, a equals 7. And then once you get it set up, so there's the 1/3, pull that out. Once you get right here, that's when you can kind of worry about what form it's going to be. So in other words, I didn't have to realize it was going to be arctan before I started. I didn't have to know that. But now that I've got to this point, I need to know that. So you see that fits right here perfectly. So this one is 1 over a inverse tan or arctan. This time I used inverse tan, so I'm just kind of mixing it up to show you that either form is acceptable. Maple always spits it out in arc. So that's perfectly fine right there. So we have the 4 from 12 times 1/3. 1 over a is 7, so there's a 1/7 there. And then tan inverse of u over a. So 3x is u, a is 7, and then plus, of course, plus c. Now the next one, I put the x in there. I won't go through every step on this one because it's pretty straightforward, but the important thing to remember, though, is the difference here is because we have du over u to the first. And when you have du over u, that's natural log. But sometimes I'll see students use du over u to any power and call it natural log. That's not correct. And this is a perfect example right back up here. Well, I brought it up, but it would have been du over u to the 1/2. Brought it up, made it negative 1/2. But if you do the same thing here and bring it up, u to the negative 1, that power and that power only has an antiderivative of natural log. So be careful, don't just call anything that's over u to any random power, don't call it natural log. It's only when it's u to the first. All right, and then there we have, so 2/3 natural log of the absolute value of 49 plus 9x squared plus c. Now, when you have integrals that are what's called improper fractions, and improper fractions in algebraic form, I mean, with regular numbers, it's pretty easy, like 12 over 5. But in these polynomial type problems, now you won't have this issue with square roots, so it's only going to be when they're polynomials, is if the exponent on top is greater than or equal to the one on the bottom, or equal. If they're the same power, you have to do long division before integrating. So sometimes students have a little trouble with this. It's not too bad, but worst case scenario, you could always probably find another video on YouTube that, long division of polynomials or something if you want a deeper explanation of this. But I'll walk through this one real quick. So there's the dividend, I believe the term is called, and divisor, and then we have quotient and remainder. Well, I went ahead and added these 0x squared and 0x as placeholders, so stuff would line up underneath it. So you look at the largest term of the divisor and the largest term of the dividend. 9x squared goes into 18x cubed, which you can just write that off to the side, obviously. It's basically 18x cubed divided by 9x squared would be 2x. So you take 2x times 9x squared, so those terms better match right there because they need to cancel. That'll be 18x cubed, and then 2x times 49, so you see I lined that up over here with the other x, make it 98x. So it's very important to realize here, as I wrote in green, just like if you were doing division back, elementary school or whatever it was, you subtract when you divide. So whether it's numbers or variables or whatever. Let's see. You subtract, so that means these cancel, and there was nothing here. So that's what makes this, see, so it's 0 minus positive 98. That's what makes that negative 98x. So you have to be real careful with that. And then once your part down here, in this case, is negative 98x, once your power is less than the largest power of the divisor, that means you're done. That means the remainder will be this negative 98x over that divisor. So the quotient is 2x, so we have to integrate 2x plus the remainder, which is negative 98x divided by the divisor, 9x squared plus 49. All right, so this one is not going to turn into arc. Obviously, if I did this with the potential, it could have turned into arctan. It didn't in this case. Still good to know, obviously. But antiderivative of 2x, that's a no-brainer. That's x squared. This one you use u substitution, but it's going to be natural log because you have du over u in the integral right here. Over u to the first. That's the key. U to the first. So if you get the division right, this is not a difficult problem. So there we have this. Du over u is natural log, so that fraction reduces. I have x squared minus 49 over 9, natural log of 49 plus 9x squared plus c. All right. Here's another one with division. Okay, this only has one division step, but it's going to lead to arctan though. 4x squared goes into 8x squared, and anytime that you have a number up here, that means that's your last step also. So this one's not too many steps here. So 2 times 4x squared is 8x squared. Those match like they're supposed to. 2 times 17 is 34, but because this is subtraction, we have negative 34 there. So our quotient is 2 plus the remainder, negative 34 over 17 plus 4x squared. All right. Now we have, so the antiderivative of 2, of course, is just 2x. But now we're set up, this is definitely arctan form right here. Fits that arctan form perfectly right here. So, of course, the negative 34 can just come out. And if this is 4x squared, u would need to be 2x, and therefore u squared is 4x squared. Now, a lot of times you see problems in books. You make a lot of them where these numbers here, a squareds, are perfect squares. But there's no rule that says they have to be perfect squares. Like we did one of the ones we did up here. What was the other? Arctan was, well, there's 9x squared, so that was a perfect square of 3x. I'm sorry, 49. I'm sorry, 49 is a perfect square of 7, but there's no rule that says you have to do that. So there's nothing wrong with a squared being 17. And then if a squared is 17, that makes a equal the square root of 17. So there's nothing wrong with that. So you have 2x minus the 1/2 coming here from the du part that comes outside. So the negative 1/2 and the 34 is going to make negative 17. And then the 1 over a is the square root of 17 on bottom. So I went ahead and multiplied the constant times the 1 over a. And it's arctan of u over a, 2x over square root of 17. Now, I'm not the least bit picky about rationalizing or simplifying denominators. I mean, yes, 17 divided by the square root of 17 is the square root of 17. But if that was on a handwritten exam, it would be fine to leave it like that. Now, on a multiple choice exam, you might see it then reduced down to the square root of 17. But I mean, obviously, it wouldn't trick you and have both those answers there. So yeah, but I don't care if you're handwriting it about whether or not it's rationalized. So there we go with that one. All right, one more of these division ones. And so x to the fourth goes in x to the fifth x times. So you take x times both of these. X times x4 is x5. X times 16 is 16x. Notice I didn't bother to write all the other 0 placeholders in there. You know, too much trouble. And I knew I wasn't going to need them anyway, so I didn't put the 0, x4, 0, x3, 0, x2, that sort of thing. But it is subtraction, though, once again. It is subtraction, so it'll be negative 16x. So that means this fraction x to the fifth over 16x to the fourth is the same thing as saying x minus 16x over 16 plus x to the fourth. All right, the integral of x dx is simple enough. Just use the power rule, n plus 1 over n plus 1. That's 1/2 x squared. Well, let's look at this integral. Let's look and see what we got here. So once again, before we worry about what the answer is going to be, let's make sure we get it set up just right here. So once again, my thought process here needs to be, okay, I need u to be something that the du will be x to the first in the numerator. Well, okay, the easiest way to think about that is if you're trying to differentiate something to end up being the first power, it needs to be the second power, because obviously you subtract 1 from the exponent when you take the derivative. So, and there's no coefficient down here of the x to the fourth you have to really worry about here. So that means u would just be x squared, because it will serve two purposes. U squared will be x to the fourth, and then the du gives you the x in the numerator that you want. So that's how you approach this. You know, the du needs to give you the correct power in the numerator, and u squared needs to give you the correct power for the x term in the denominator. So now, of course, we have to adjust for the 2, but that's no trouble. Divide both sides by 2, and we got it. So 1/2 du will equal x dx. So we already have this first part, then we have 1/2 du. And that'll give me 8 minus 8. And then now it fits tan inverse, because it's du over 16 plus u squared. So this will simplify to 2, because what's happening here is, you know, I have this the 16 times the 1/2 make the 8. That's assuming the same negative there. And then the 1/4 is coming from 1 over a, because a is 4. So 1 over 4, so I just combine that. So it's the 8 and the 1/4 make that 2 right in front. Of course, it's negative 2, but it's 2. Now then it's arctan of u over a. So it's arctan of x squared over 4. Okie doke. Let's see. Let's take a look at this one. Same kind of logic the last one. I kind of just to mix it up a little bit, I just reversed them in the denominator. See, with addition, you can do that. Now, subtraction's totally different, you know, totally different thing. You know, we'll see some other examples coming up down the road and others starting even in the next section that we do, but I'll follow the video to this one. But subtraction's a you know, tricky deal, because, for example, you know, like a squared minus b squared is not the same thing as b squared minus a squared. But that's not true with addition. So, you know, obviously, even though the formula is written like this, it's just as accurate as if you have u squared plus a squared on the bottom. It'd be just the same thing. So I kind of mixed it up here. Throw you a little curveball. So, but same principle applies. I'm looking for something that when I take the derivative of it, it'll give me square on top, and then when I square it, it'll give me 6. So obviously, t cubed would be the correct power for u here, because the derivative of t cubed will give me 3t squared, and then divide both sides by 3. So then now your numerator t squared dt can be replaced by 1/3 du. And then, of course, u squared then will give you that t to the 6 on the bottom. And then a will be the square root of 16, which is 4. So now it fits the arctan perfectly. So there we go. So the 1/3 comes from this du adjustment. 1 over 4 is 1 over a is 4. 1/12, so it makes it 1/12 arctan of u over a, which is t cubed over 4. And that would give you then what I have. Well, there's that same thing. Well, obviously I didn't multiply them together to get 1/12, but obviously it's the same answer. 1/12 of t cubed over 4 plus c. I don't know. This one seems a bit redundant to one of the ones I did earlier, I think. So I'll just maybe leave it up here on the screen for a minute and let you look at it. That way you could pause it and look at it before you moved on. But I'm not going to go through this one really. Not too much to it. Because it ends up being natural log. You know, I'd be probably more interested if it turned out being, arctan, since we're learning something new there. So you can obviously freeze the video and take a look at this one if you want to. But it's very similar to one of the other ones I did. Now, okay, we're getting something. This is a little different here. So we haven't used the inverse secant yet. So this one's a little interesting. Let's see what I did here. Now, this one actually I do need to kind of bring the formula in a little bit earlier. You know, before I was telling you to don't worry about the formula until after you get everything set up, but you will kind of need to look at it. Because now we know that to be 9x squared, u has to be 3x. To make that square be 9x squared, and the du gives you the 3 on the top. 3dx makes it 1/3 du. But now, it's not quite in this form just yet. And that's where those red 3's are coming from. I'll tell you what that is. You see it has u out there. But u had to be 3x, correct? Because of the 9x squared. The u has to be 3x. So, and this is u out here, but you see it was only, the original problem only had an x. So guess what? I had to force a multiple of 3 in there to make it 3x, so that way it ends up being u. And then, of course, anytime that you modify the numerator or denominator of a fraction, you have to do the same thing top and bottom, because that way you're just multiplying by a different version of 1. So the 3 on the bottom was necessary to make it 3x, and the 3 on top is to balance it out and keep it the same value overall. So there we go. So that was a pretty sneaky little trick there, but now you know how to do it. So what do we have here? 1/3. So there's going to be a 3 times 2. It's going to be a 6, which is right here. That's 3. And there's the 1/3 du. So those two together multiplied will be 2. And now it's perfectly in this form. So we have 1 over a. I didn't write what a is, but I'll say right here. Square root of 25 will be 5. I know some problems I wrote, like sometimes I wrote what a was, but I guess I didn't here. But no harm. A is 5. So it's 1 over 5. Sec inverse or arc sec, whatever. Absolute value. Go ahead and use absolute value because the formula has it. Absolute value of u. So it's the absolute value of 3x over that a, which is 5, and then plus c. And then all I did here was just combine the 2 times 1/5 to give it 2/5. Okay, now here's another one. It's got a little sneaky little trick to it there too. I'll move this over a little bit. All right. Now this one's a different kind of problem. I mean, u pretty much has to be x squared here. Because that way when you square it, you get x fourth. But when you take the derivative of x squared, you get 2x dx. There's no x on top. All right, we can fix that. Now, one of the most important things you should have learned in integration in Cal 1 is that you can never, ever, ever pull the integration, variable of integration, which dx tells you x, outside the integral. Like pulling that x out of there is completely wrong. You cannot do that. However, you might not have learned this, and it probably didn't apply. I know I usually don't talk about it in Cal 1, but there's no rule that says you can't multiply the integral itself as long as you're not pulling it outside the integral. by variables. So I can do sort of like the same thing I did in the last one with 3 over 3. I can just do it with x over x. That is actually allowed to do. You can do that. So there's something you might not have ever seen before. Probably wouldn't have the need to, like I said, but now that makes everything fall into place because it solves 2 of our problems. First, it gives me the x squared that I need on the bottom to be u, and then it gives me that x on the top that I needed for du. So that was obviously necessary that we multiplied that by x over x to make that work. And now it just fits perfectly. Now everything's great. So we got a 1/2 du representing the numerator. And so that's this first 1/2. And the second 1/2 comes from the formula, 1 over a. So this 1/4 comes from the fact you have 2 1/2s multiplied together. Like I said, one from there and one from this 2 being right there. So 1/4 arc-seq of the absolute value of x squared of u over a, which is 2, plus c. So a couple little interesting techniques there, I think. All right, this problem's kind of weird. But let's see if we can give it a whirl here. Now, with all that stuff on the bottom, it looks like it might be some sort of arc-seq, but it won't be because you have to have 2 terms under a radical there. So anyway, to kind of get this cleaned up and get it in some form where I can deal with it a little bit better is, well, first of all, I took the 3 2.5, put it out. In this case, I want to bring the x, square root of x up. I was thinking try to distribute this on the bottom, which algebraically it is allowed because that's to the first power in parentheses, so you could distribute, but it does you no good from an integration standpoint to do that. So you would not want to do that. So the square root of x comes up to make it x to the negative 1/2 and 15 plus x. Now, here's something I haven't told you yet, but I'm going to tell you now. You know, when you're thinking about these formulas that have, u squared, you're expecting the variable to be something that's squared, like 9x squared or 16x to the 4th or something where we did one earlier, I believe there was a 4th there, power x to the 4th. So you expect that to be an even number because that seems to make sense because when you square something with an exponent, it's multiplying its factor by 2. Like for example, x cubed squared is 2 times 3 is x to the 6th. But you can actually square things and get an odd exponent, x to the 1st. Basically, you're thinking about what is the square root of that. In other words, think of it like the square root of x to the 4th would be x squared. So this one, you think of it as u would have to be the square root of x, or x to the 1/2. Because if you square x to the 1/2, you'll get x. So that's what's going to happen anytime that you have an odd power here. That means your u is going to be raised to something over 2. So like, for example, if this was x cubed on bottom, you'd have x to the 3/2 here. So that's kind of sneaky. I can see where that would maybe throw some people off. And it works perfectly here too, because now, that's why bringing that square root of x up makes it easier to see. You now have, take the derivative, that gives you x to the negative 1/2. And now it fits perfectly with what we need. Of course, there's a 1/2 there in front too, but that's easy to deal with. Move it over, make it a 2. And so that's wonderful. That gives us the x to the negative 1/2, and we're taken care of on bottom. So we got u squared. A would be square root of 15. And then the du is 2. So I brought the, let's see. Oh, I didn't show it here, but let me just tell you. So there was a 3 over 2, but the 2 here would have been up there and canceled that 2. I guess I didn't write that in there anymore. Sorry about that. But there's the 3. But the 2 cancels out with that 2 right there. At least I can point at it and show you. So, all right. Must have missed putting that step in there, didn't I? Oh, well. We're okay here. So now we have just the 3 left here. So it's going to be arctan 1 over a. So it's 3 over the square root of 15 arctan of u over a. So u is the square root of x. Obviously, it doesn't matter to me whether you put the square root of x or x to the 1/2. They're both acceptable over the square root of 15. As I said before, on a handwritten test, I would not care. That's why, anytime I put like a check or a flag mark or some school logo next to an answer, that means I consider that to be acceptable form for an answer. Maple is programmed to rationalize a denominator, so that's the only difference. All right, these problems are interesting. I like these, where you have to split them into two pieces. You can't really use one integral to take care of the whole thing. You've got to split it up. So once you split it up, then it's not too bad. So could have been a little tricky, I could see at first, trying to figure out how to get this thing started. Because that's plus in the numerator, I'm allowed, algebraically to split it up. Remember, you can't ever, a lot of mistake I'll see students make is you cannot split up multiplication. Let me see. I'm not working on a tablet PC here, so I can't really write, but I can sort of freehand. So you can't say that, in other words, the integral of f times g is not equal to, thank goodness my notes don't look like this, f times g. In other words, you can't do that with integrals ever, but plus you can. So if I get rid of this and put equal here and make that a plus, then we're in business. Okay, so let's clarify little mistakes like that from time to time. Things we do not want to do. So let's kind of look at that first one. So you see that first one's got that x in that numerator. So the way I'm looking at this is going, all right, I know the derivative of x squared will produce an x, but I also know the derivative of 4 minus x squared would produce an x. So that's the decision you make then. Since they both produce that x, you want to include the 4 with the u. You want the whole thing to be the u. So you let u be 4 minus x squared, which makes du equal negative 2x dx. So you make it negative 1/2 du as x dx. And so that one's just going to be a power rule for substitution. This one's already set up pretty well for arc sine because it just has x squared there, no coefficients or anything. I'm just using a different letter here for substitution. I wouldn't require that on a handwritten test that you have to use two different letters, but just visually, I didn't want to have a u here, confuse people, so I decided to go with substitution. Let w be x, du will be dx, and then a will be 2. So the one on the right fits arc sine perfectly, and the one on the left will just be u substitution. So we have 4 from the numerator on the one on the left, times the negative 1/2 makes negative 2, du over u to the 1/2, and then we bring that up, makes it u to the negative 1/2. Come over here, this one's just dw over square root of 4 minus w squared, so it's just arc sine of u over a. Remember, this one, unlike the tan and the sec, doesn't have the 1 over a in front. So it's just 3 times arc sine of x over 2. Over here, I'm just writing out the antiderivative of u to the negative 1/2 just to show you what it was there. So actually then, so that antiderivative produces a 2 right here. So this 2 that I'm pointing at in red there combines with that negative 2 right there to make that negative 4. And then it's just 4 minus x squared to the 1/2. Whether you have a radical there or not makes no difference to me. Plus 3 arc sine x over 2 plus c. And there we go. Alrighty, so now you see the trick on these is to split them up. Here's another split them up. Except this one's going to have arctan in it this time instead of arc sine. Split them up. The first one is because we have an x squared and an x, we'll let u be the entire denominator. X squared plus 25 gives us 2x dx. So it's 1/2 du as x dx. And this one on the right perfectly falls into arctan. Not too much work to do there. with w being x, dw is dx, a is 5, so it's good to go for arctan. Now let's finish this one on the left here. We have a 3 right there, and we have a 1/2 here, so those two make 3/2. Now, remember, this is du over u. Unlike the last one, which was du over u to the 1/2, and I mentioned this earlier in the video, you use a power rule. Only when it's du over u to the first does it turn out natural log. Anything other u to the first on the bottom, it's power rule. So that becomes natural log of u, and this is arctan. So it's 2 over 5 arctan of w over 5. So let's see what we have here. So it's 3/2 natural log of x squared, absolute value of x squared plus 25, minus 2 over 5 arctan of x over 5 plus c. All right, here's a definite integral. Not too bad. It's just it's an arctan form already, because you got to be careful here though. Like for example, if that would have been, let's see if I did that well. Okay, I had that coming up, so I'll wait and save that. But you let u be sine, not the entire denominator, because I see people mess up. The derivative of sine squared is not like 2 cosine of x or anything like that. You want u to be sine only, and that way du is cosine, because that way you can let that be u squared right there. So you just let u square the u, and that's how you take care of that. Now I'm a big fan of indefinite integrals, of changing the limits of integration. Makes it easier. So I'll put in the upper and lower limits in for u, because once you change this over to u, that way you never have to go back to x for any reason. So sine of pi over 2 is 1, sine of 0 is 0, so now we're going from 0 to 1, du over 1 plus u squared. And so it's arctan of u from 0 to 1. Arctan of 1 is pi over 4. You can get that off of a unit circle. Or if you do it in the calculator, put it in degree mode. It'd be easier to interpret, because if you get a degree, you see 45 degrees, and there's how you would convert it to make it pi over 4. If you do radian mode, it's going to show the decimal answer to pi over 4, which is something, I don't know, whatever, 0.7 blah blah blah, and that might not be as helpful as seeing the degrees. So you end up with pi over 4, so the answer is pi over 4. And this is just kind of showing you different stuff here. Some of this stuff we'll see later. Now this could actually, whenever you use natural log integration, which we've already possibly done before, whether you did it in Cal 1 or you did it early in your Cal 2 class, whichever the case may be, but this time you let u be the entire denominator, all of it, and then that way du is cos x dx. But that would not have worked for the last problem, because actually the derivative of sine squared is actually 2 sine x cos x. So that would not have worked. So this ends up being a natural log here. This one, we'll talk about this technique a little bit. This theoretically could have been done in Cal 1, like show that, because it really doesn't involve anything that fancy. But we might see something. We'll see. In other words, we'll see conjugating stuff here coming up in another chapter. But anyway, this one could have been done in Cal 1 if somebody really wanted to get tricky with you or something. I probably wouldn't have done it. But you have to rewrite cos squared as 1 minus sine squared, and then factor it out as a difference of 2 squares. And then you get a 1 minus sine of x, 1 plus sine of x, and then those two cancel. It's just left with 1 minus sine x. So the antiderivative of 1 is x, and then the antiderivative of minus sine of x is positive cosine of x. And so you have x plus cos x plus c. Now here's one using e's that turned into arctan. It's kind of interesting, because in this case, to get e to the x dx, and then in the numerator we want u to be e to the x, because the derivative of e to the x is e to the x. So I'll let u be e to the x, which actually makes u squared equal e to the 2x. You have to be careful here. E to the x squared is not e to the x squared. It's e to the 2x. You multiply the exponents. So u squared takes care of that one, and it just falls right into perfectly into inverse tan. du over 4 plus u squared. So you have 1/2 arctan tan inverse, however you want to say it, e to the x divided by 2 plus c.